Hi everybody and welcome. I'm Dave Yelovic. I'm the chairman of the Education Committee here at the Greater Houston Builders Association, and I'd like to welcome you to our online edition of our ABCs of Home Building Education Series. We offer these classes at least one or two a month at the GHBA in Houston if you'd like to join us. Check the website. You can see when we do these live, you can check there for a full schedule. But again, look for that or any of our education classes that we've got going on there all the time. Here, we're live and, well, kind of live, but we're on your computer. And during this discussion, if you ever have a question, you can reach me at dave@daveyelovic.com. Just spell Yelovic right, but dave@daveyelovic.com. And I'll try to answer your questions as soon as I can, whether it's during this video or perhaps when you go out into the field, when you see something that might revolve around the topic that we're covering. If you got a question, I'd love to help you out. Just feel free to call me or write me. As you can see, I've been doing this for quite a while, 30 years in residential construction. I've been at the GHBA for a while, and I also do a lot of code work. I'm on the code committees for TAB and the NAHB, and I do a lot of instructions for many different groups. I'm glad you're here, and I hope you're going to have fun and we're going to learn something. I've got one objective in all these classes that we do at the GHBA for the ABCs of home building is to give basic education to those that are taking the class, again, either live or online, basic information about the topic that we're going to cover. Today we're going to talk about framing. And in the framing, there's a lot to do with the 2018 IRC, the International Residential Code. So from time to time, you'll see code references on the screen, or I'll put them up there on the video. But that's the idea, is that you as a superintendent or you as a home builder, you go into a job, and in this case, you'll go into a frame and you want to know, is this a good frame or is it a bad frame? Or maybe not just a really good frame. I hope no one has a bad frame. But you'll be able to go in and see what's right and what's not. The ABCs of Home Building series is all about that. Whatever we're talking about, just being able to go in and see what's right and what's not, and be able to punch out the work like a true professional. That's our objective in these classes. So let's not take any more time. Let's jump into framing. It's one of the biggest things we've got. So after concrete, we've got a slab in the ground, and now we're going to frame ourselves a house. So let's talk about the basics. It's pretty simple. In order to frame this house, we're going to need a set of plans, right? The first thing I would do as a superintendent when I get issued a job is I would check, obviously, selections and other things, but look at the plans, check change orders, make sure there's no changes or someone has flipped the house or whatever might have come up. Challenge yourself and say, are these plans correct? Everyone does a great job getting these things out to the field, but occasionally mistakes will come up. So become familiar with whatever that plan is. Go through it, add up the dimensions, make sure everything's right. Try to find the mistakes ahead of time. So we're going to have at least a set of plans, a plot plan, and then we're going to have some elevations. Elevations in this simple thing is just showing us an illustration of what this is supposed to look like. So if you give the framer a set of plans and some elevations, he can create this thing from basically a slab and a pile of wood. He can create this house. So again, I'm checking the basics. I check the plan, I check the dimensions, make sure everything's going to work. And I look at the elevations, make sure I'm familiar with them. And then I get into the details. So here, just for fun and adventure, here's the front elevation. It's pretty simple, little one-story house. It's got a front elevation with some shutters on it. It's got a little gable roof over the entry. Pretty simple kind of stuff. So I'll look for that and say, I can do that. And so I might flip through, go through the floor plan, go through the framing plans, and see how things compare to what this thing is supposed to look like in elevation. So while I'm looking for the plans, plans are great, but I often tell people that unless you check the notes, whether it's on the foundation plan, the framing plans, there's some notes. They're usually down at the bottom or up on the top somewhere. Look for the notes because they tell you a lot. In this case, it tells us all sorts of things. The beams are to be number 2 southern yellow pine. We'll talk about that in a little bit. Rafters are supposed to be 2x6 southern yellow pine number 2. So it tells me a lot of stuff without having to be on the plan. it tells me some things. Purlin Bracing, and here I put a question mark, just simply Purlin Bracing. We'll get into that when we talk about span charts and things like that. But so I look at the notes because sometimes on a plan, you'll notice the plan, at least here for the roof framing, there's not a lot of lines on here showing me what the roof is made out of. It tells me 2x8s at 19.2 on center number 2. So that's different than the notes, okay? But then everywhere else, maybe there's not any of these notes. So per the notes, it's 2x6s. So read the notes to get an idea of what the overall job for the frame might look like. So, and then look at the details. Any good architectural set of plans has some good details. The framer will look at these to say, how far, in this case, is my overhang? What's the angle of the roof? What's the pitch? Lots of things are noted on details, so become familiar with those things. So plans, elevations, details, notes, all these things you should be familiar with. So when you talk to the framer, it becomes a conversation and you're both talking on the same page. So earlier I showed you an elevation, and it's of this house. And I could look here and say, oh, here's the frame that I'm doing. And I could tell here this is going to be a hip roof, meaning the roof is kind of sloped backwards over that front entry on the elevation. But if you remember, let's see if I've got it here. No, let's go back. But remember on the front elevation, it was a gable. So right there in the set of plans, I have a discrepancy. So I've got an elevation showing a gable, and I've got a plan that shows a hip. So the framer is probably going to put a hip on that, or a good framer will come to you and say, hey, I've got a conflict between these two things. Is it a hip or is it a gable? Those are the types of things as a superintendent you can expect out in the field, and that's your job to iron all those things out. It may require a phone call. Maybe you talk to sales, maybe to the design crew, whoever's responsible for these, but you get them ironed out. So get them ironed out before the work happens. It's not good when it's framed up and the client comes by and says, no, I'm supposed to have this type of elevation. So check your plans. So now we get to going. So we've checked the plans, we're ready to go. Some basic stuff about lumber. We call it dimensional lumber. We talk in terms like 2x4s, 2x6s, 2x8s. Just so everybody knows, that's not what they are. There's actually lawsuits about big box stores selling this stuff, and they deceive the public because a 2x4 isn't really 2 inches by 4 inches. Here I put the regular dimensions because from time to time you'll have to add up on details the exact space that's needed for an assembly. Maybe it's a corner or a column or something, and you have to know the exact dimensions of everything from the sheetrock that's going on it to the actual lumber. So when we say 2 by something, it's actually 1.5 inches in thickness. Alrighty, that's all the lumber we use is always 1.5 inches thick. And then 2x4, 2x6, 2x8. 2x4 is 3.5 inches. 2x6, 5.5 inches. Those two are pretty regular. Once you get above a 2x6, it's 1/4 inch. 2x8 is 7.25. 2x10 is 9.25. So you know how it's going. This comes into play later on also when we talk about notching and boring, when it says you are allowed a certain amount of the actual depth of a member. You have to use the actual depth. So these things will come into play later in the presentation. So then we go forward, we're going to talk about different products. Not everything is dimensional lumber anymore. Many years ago, yes, all you had were 2x4s and 2x12s and things like that. But now we have the miracle of technology has given us engineered wood products, or EWP. Anything that's made in a factory is considered EWP, engineered wood. Lumber is cut from a tree, is pretty straightforward, it gets kiln dried, and we're very happy with that. But technology has given us this wonderful stuff called EWP. Whether it's OSB, oriented strand board plywood that we use on sheathing for walls, on our subfloors, maybe up on our roofs, we use OSB everywhere. That's an engineered wood product. We also have things like trusses, whether they're floor trusses or roof trusses, they're made in a factory. So that's an engineered wood. And then we've also got beams, whether they're beams or other things that are made in a factory. Again, they're made of different products. Some are laminates, some are pressed together and epoxied, but they're remarkably strong. They don't bend much, they can hold a lot of weight, and they've opened up the design of residential construction because we can make great spans now with things that we couldn't do before. So we'll see some more things that we use that are considered engineered wood. So one of the basic things on our lumber we talk about is the grading of the lumber. When it says number 2 lumber, where does that come from? And when we look at these things, we'll see on every piece of lumber, dimensional lumber, there's supposed to be a grade stamp. And if the plan calls for number 2 lumber on headers or on ceiling joists, your inspector may walk along and look for that number 2 stamp on the lumber. And so you should get used to doing that too, because there's number 2 lumber that we use and number 3 for the most part here in Houston. But look for the grade stamp. Some will be very simple like this. I won't go over the entire list here, but we're looking for is a KD, which is kiln drying, and is a SYP, Southern Yellow Pine. That's usually it. And then it's going to be number 1 or number 2 as depicted here, number 1, number 2, or number 3. So that's what you're looking for in a basic grade stamp. So that should match what's on the plans. The other thing, so obviously we've got wood, we've got engineered wood, and now we've got nails. This is kind of an interesting thing because in nails, there's all sorts of nails in the world, but the code book has a lot to say about nails, and it's kind of interesting. So our 3 basic nails are 8 penny, 10 penny, and 16 penny nails. And you'll notice the 10 penny nail is about 3 inches long. And then the 16 penny is about 3.5 inches long. Those are some big nails. Now, you would think, hey, what's the big deal? You'll see later on when we talk about roof assemblies, wall assemblies, headers, the code book has a schedule of how many nails and what kind of nails are needed to put all this stuff together. And you'll see some of these coming up later on, but we should be familiar. What is the most common? The most common nail we're going to see used in the code book is a number 10, number 10D, penny, and it gives us options. It's this nail or this nail or this nail or this nail are the options we get. And then the number 10 to me is the most common. I tell people if you're punching out and your framers are framing, go look in the trash heap. Look at the boxes that are left. What is described in there? So besides 10 penny, box or common, there's also this one 3-inch by 0.131 mentioned in the code book. A very common nail. You find it on all sorts of job sites. But you look on the label, just simply know that's what they're using. Then you have an idea of at least what's in there. Can you measure what's actually in the wood? No. You'll see a nail head, but that's all you know. So now you can look in there and then also know that most framers are usually using 10 penny or 3-inch nails, and you can tell by what you find on the job site. So real briefly, before we start the house, so we've got the plans, we've looked over everything, we're happy with it, we've got material coming, and now we've got a job site. You're in charge of that job site. So a word about scheduling. How long will this job take? To frame a house, have you talked to your framer? 1-story houses probably get done quicker than 2-story houses. Smaller houses get done faster than big houses. But how many days? How do you get all your material there? Do you drop material all at once, or do you stage it out as the framer needs it? I'm a big fan of staging it as it's needed. 1, it doesn't get rained on. 2, it doesn't get stolen. 3, he doesn't intermix pieces, so if you're short, you know what's short. So check with your framer. If it's a 5-day job, maybe it's a 2-story house, have it staged out maybe with 3 deliveries. Spread it out, maybe room on the job site won't accommodate all that lumber. So you have to spread it out over time. So keep that in mind. Talk to the framer, see how long it's going to take, how much material can you put on the job site, and when do you want to have it delivered. So look at that. That's the schedule. Then what about the crew? Has the crew been notified? You got lumber coming, you've poured the slab, you've got lumber coming next week. Have you talked to the crew and said, hey guys, we've got lumber coming, and giving them the date, maybe the plan, and go from there. And then finally, do you have power on the site? Power is a big deal. If you don't have power on a site, your framer's going to need a generator, and that's always not fun because it's going to charge you extra for a generator probably. So make sure well in advance, as soon as you know that job is coming, make sure you got a temporary pole out there, you've applied for the meter, you've got power out to the job site, so when the lumber does drop, they can plug in and go from there. So we're just about ready to start framing a house. Alrighty, so here we go. We've studied our plans, we've talked to the framer, we got lumber coming, we got power on the job site, we got a slab poured, we're ready to go. And really, guys, the only thing we need to know is, hey, this all starts with strings and chalk line. This is where the rubber meets the road. How well did you punch out that slab before you poured that concrete? Well, your framer is going to tell you, is it out of square? Are the pipes in the walls? All that takes place the very first few hours of framing. He's going to take a set of plans and he's going to duplicate that with chalk lines on the slab. It's a pretty simple process. And then obviously he's just got to make the walls and work up from there. But this is where you're going to start figuring out how good your slab was. So it starts with just framing a basic wall. They're going to frame it on the ground or on the slab, and they're going to tilt it up in place. He's going to build one wall at a time. This is a very long wall. The exterior walls usually go up first. And so this crew has framed it on the wall, and they're all going to stack it up together, and away it goes. So that's actually a pretty fast process. It's kind of fun to watch a frame go up. If you've never seen one, hang around, sit in your truck and watch them do it. But then we start going along and we start putting up more walls. As we start putting up more walls, think about, this is the weakest part of a frame's history, is when it's just being put up. You need a lot of temporary bracing. If you look in these pictures, we've got temporary bracing. We've got 2x4s pointed in all directions. We've got them on the outside of the house. We've got them inside the house. We've got them holding up walls, and that's great. A house that's not properly framed at the beginning is in danger of falling down on any given day. All it takes, we call it racking. Take an afternoon thunderstorm in a summer afternoon. Everything seems to be fine. Whip up a nice wind in the afternoon. It hits those new walls, and the house will rack like a bunch of cards or dominoes, and it just falls to the ground. We're going to see how we resist that in a frame, but while it's just a bunch of 2x4 standing straight up, you can just go over it, push it, and it'll want to fall down until we get it rigid. Temporary bracing helps us do that. So if you've got a bunch of walls up on a house and there's no temporary bracing, talk to the framer and say, hey guys, we need to brace that, because again, whether it sits overnight or a storm comes up in the afternoon or just gravity, walls can fall down for any given reason. So we're going to start at the bottom, and obviously when they tilt that wall up, there's a Soleplate. That's the bottom 2x4 or 2x6, whatever the wall size it is. But we're going to say that's the Soleplate or the bottom plate. And they're going to start, and we're going to put anchor bolts. Concrete class, we learned we're going to put anchor bolts. They're going to be sticking up about 3 inches. They're going to be in the middle third of the bottom plate. There's going to be a nut and a washer. Okay, nut and washer, that's it. So when he tilts it up, eventually he's going to plumb it, straighten it, and then crank down on the anchor bolts to make sure it's there forever and ever. The other option you have is a mud sill anchor. This is another approved way to keep a Soleplate down to the slab. And those simply sit on the outside. They bend them over, and then they'll put nails into those. Usually 4 to 6 nails in those, depending on which one you're using. But before we even get to the wall going up, the very first thing the framer does has nothing to do with framing, has to do with the energy code. But we have to make sure that he knows the energy code. So all framers now, for the most part, we're putting down Sill Seal, which is a styrofoam gasket, maybe about 1/4 of an inch thick, all exterior walls, including the wall that butts up to an attached garage. Anywhere exterior air can infiltrate under the bottom plate and into the house gets this little foam gasket. So then the wall tilts up on it, he cranks down on the anchor bolts, and that creates a gasket underneath that to keep air infiltration from coming through that point. Very neat little thing. It'll help you on your blower door test. Nothing to do with framing, But to pass that blower door test, you're going to need that, and that's a framer's job. So parts and pieces. I may put this up on the screen, get a little close up, but if you're going to talk to professionals about a frame, learn the terminology. Don't talk about thingamajigs, or you see that thing there, or hey, that thing up in the top of the, you know, where the rafters come up and join at the top. What is that thing? Oh, the ridge. Get to know the parts and pieces. So if you're talking to the design team, you could talk logically about the frame. If you're talking to the framer or an inspector or even your clients. But get to know what we're talking about. So in a simple wall, obviously we've got studs, regular studs. What's a king stud? King stud is the one next to the opening that we've got here, where we've got trimmer studs, the ones that we cut up, let's say. And then we've got our sill, jack studs coming in here, or cripple studs as some people call them. And then headers. What's the job of a header? We'll see some headers in a little bit, but the job of the header is to do just that. All the weight that normally comes here, it's going to pick up that weight and transfer it to the outside, come down those cripple studs and transfer that weight down into the slab or down into the structure somehow. So a header transfers weight to the outsides and transfers it down. So it has an important job in a frame, but know the terms. So what's a header look like? When I look up at a header, there's maybe two different situations. Now, again, in an energy code situation, I have a header that may look like this. It's a 2x something, and again, it's on the plans. It might be a 2x double, or 2x6, 2x8, 2x10, 2x12, depending on the load that's on top of it. And then there's a spacer, and then there's another 2x after that. So it's a sandwich, okay? Double 2x sandwich with a 1/2 inch material. So 1.5 inch, 1.5 inch spacer. That makes a 3.5 inch header, which happens to fit perfectly in a 3.5 inch 2x4 wall. That's why the spacer's there. The spacer used to be just OSB blocks, just plywood blocks put in there to make a space, and it'd be open air through there. Now the energy code says, hey, that's not good anymore, so we fill those up fully with insulation board. In this case, the insulation board's blue, but it could be pink, could be any other color. But it's a little bit about R3 worth of insulation in the header itself. So that's an insulated header. Those go on the exterior walls. Interior headers, you don't need insulated headers, so they can just use spacers, those OSB or 1/2 inch blocks between the two 2x, nail them together, and it's still 3.5 inches wide. So that's the difference. Two different types of headers, one exterior wall, one interior wall. There's a note I just want to bring up. In the newer codes, like the 2018 IRC, it is allowed to have different kind of headers. You don't have to have that double sandwich like I just talked about. You can have a single member header. A single member header might be a single 2x12 with maybe a 2x4 underneath it, nailed together like a giant L. That's a single member header. There's a whole section in the code book that talks about using those. That's a great way to get more insulation above a window or door on the exterior wall. Or if it's not a load-bearing opening whatsoever, you'll see a lot of interior headers that have absolutely no load on them. But we'll put, in the old days, double 2x12s over them because we thought that's what a header needed to be. But if there's no load on it, the code now says I can put a flat 2x4 for a 2x4 wall, or 2x6 for a 2x6 wall, a flat header with just some cripples, and that's it. I'll nail my door frame to it, the door trim, and that's it. That's its only job. It's not structural in any sense. So single member headers or flat headers for non-load bearing walls are all allowed in the new code book. So as we're going forward here, I talk about rough openings. When talking to your framer, he should know what your rough openings are. I talk about doors at first. The plan will show 2, 6, 6, 8. What does that mean? 2, 6 is 2 foot 6 inches, and then 6, 8, 6 foot 8 inches tall. So it's 2, 6 wide, 6, 8 tall. So, okay, we make, no, you got it. That's the door that's going to come from the factory. It's going to be that big with its frame and everything else. So you need an opening, a rough opening that's larger than the door itself. So normally, most doors will come and we're going to add 2.5 inches to every dimension. So if it's 2 foot 6, we're now going to make that dimension 2 foot 8.5. And then 6'8" is going to become 6'10½". So now as I'm punching out the frame, I'll go around. If I look at my plan, it says 2668. I measure, okay, it's 2'8½" by 6'10½". That's a good, nice, rough opening for a door. Allows room to move it, plumb it up, shim it, and away you go. If you make it exactly, it's not going to fit. So check door openings when you're punching out a frame. The other one are windows. If it says on the plan 3050 SHDL, single hung divided light, that would be a single hung window that opens from the bottom, and then divided light are those little crisscrosses in the window. If there's no crisscrosses, it's just SH, single hung. But this one is more manufacturer specific. A lot of companies, since we use flanged windows here in Texas, it's just a double pane glass, usually vinyl now, frame and flanges on them. The window size itself, 3050, the opening may be 3'0" by 5'0", and that's the opening. But it's going to depend on your manufacturer. So double check, whoever your window supplier is, what the rough openings are, and that'll tell you how many, if any, inches to add on the rough opening. So let's talk about walls. We mentioned earlier, we're going to measure them, start tilting them up, go from there. But what are the details? What can we look at here? So, like I said, in the code book, in table 60231 that's mentioned up here, that's fasteners for structural walls. That's in the 2018 IRC. I would put it up there, but it would be a bunch of numbers and gobbledygook that you probably couldn't see on your screen. But I challenge you, go find them. If you'd like, email me, maybe I can send you a copy. But it is a formula. It's a Betty Crocker recipe for every connection. If you're going to nail two studs together, what size nail and how many, how far on center should they be? If you're going to nail a header together with a sandwich in between, how many nails need to be, how far on center, and which direction do they go? If we're nailing the stud to the bottom plate, if we nail through the bottom plate because we're doing it on the slab, there's different kind of nailing for that as versus if we toe nail from the top like this, different kind of nails are applied by the code. How about at the top plate? How do we nail those? Double top plate means there's two of those 2x4s at the top of the wall. There's a formula for nailing those things together. How far on center should those nails be as that thing is sandwiched together? All of these things, every connection is generally covered in that code book in that table. So at least go through it, get familiar with it. I'm sure your framer probably has never read it. Maybe share it with him. But it gives you a great idea of when they're framing how all these things come together. You'll see some nails on some connections, and we'll talk about that. Some you'll never see. They disappear as the frame goes up. But if you look at something and you don't think it's nailed properly, you have a guide to help you answer any questions you have about nailing. So, traditionally, in a corner, we used to have 2x4s. I'll use 2x4s for now. Most of us use 2x4s on our walls. You can use 2x6s, but for now, let's talk about 2x4 walls. But we would take 2x4s, and we have one on this wall, one on this wall, and then we'd fill the corner with blocking and other studs so we could sheetrock this thing. That was our major concern. How do we sheetrock this thing? And now it's become more of a concern about energy. How can we make this more energy efficient? Air is not energy efficient. In this old way of doing things, this corner was filled with air, which is not an insulator. That's bad for a house as far as energy consumption goes. So this is old school technology. So as we look over here, you can see here's a traditional corner. There's no way to get insulation into that thing on down the road. So they've come up with bigger and better ways to do things. There's a number of ways. We're going to talk about California corners and ladder tees. Corners, California corners, 3-stud corners. It's all a way of making things, I say, getting more fluffy stuff in the wall. The more fluffy stuff you have, the more energy efficient it is, the better it is for your energy code compliance. Excuse me. So there are, traditional corners in here. There's a ladder tee here and double, but what we're trying to do is any way to get insulation back behind the framing members to create an insulated wall will get us to the point where we get energy efficiency. So you'll see some of these details come up, but again, all you are is simply moving the framing members to a point where you can get insulation back behind them. The most common is the ladder T, and then the California corner, where we're making 3 stud corners and being able to get insulation behind it. So what's it look like? Here's a ladder T detail. The biggest thing you want to know is coming from the ceiling down. This first block needs to be exactly 4 feet from up at the top to the center of that block, because when you lay sheetrock, it goes right up to that first block in the middle. That's where you nail to. Then you'll put 1 or 2 blocks above it, 1 or 2 blocks below it, depending on your plate height. 10-foot plate height, you need more blocks. But you don't want to exceed 24 inches on center with your blocks. But the most important ones are the one at 4 feet and the one at 8 feet, because that's the length of sheetrock that you're going to be doing. So California corners, 3 stud corners. Again, how are you aligning them? To get them down and underneath. Get some insulation in there. So that's California, or that's the ladder T. Let's look briefly, just quickly, at the idea of the California corner. Here I've got a 2 stud corner, and I'm allowed right back here where it gets a little dark back here. That's where I can stick insulation back into the wall, get more fluffy stuff into it. So that's how we get more insulation, more fluffy stuff into a ladder T and a California corner. So as they tilt up these walls, your framer is a good framer. He's going to put up some really nice looking walls. Eventually, someone's going to cut up those walls. So get to know the rules about these walls. So the first one is, we talk about in the 2018 IRC, another section, 6026. Section 6 is all about walls. If you want to find something about walls, look in section 6. But cutting and notching of walls and wall members is a big deal. Plumbers, AC guys, electrical contractors, everyone likes to cut into walls because they got to run their stuff through them. So this talks about a non-load bearing wall. So on a non-load bearing wall, how big can I make things? I can make a hole, something like this, a hole no bigger than 60% of the actual member. So remember, it's a 2x4, which is 3.5 inches. So I can make a hole that's 60% of that on a non-load bearing thing. Well, you look at the top. Does it have load on it? If the answer is no, then it could be 60%. It says, what about a notch? Can I notch this thing? Yes, you can put a notch, you can cut out a whole little notch out of it, up to 40% of the width of that little member. So, but there's even some diagrams inside the code book that walk you through this. So non-load bearing walls, you can put fairly good size hole and a fairly good size notch in that. But remember that, because we're going to come back to that with an example here in a little bit. Then there's load bearing walls. In the same part of the book, talks about load bearing walls. So for the same thing, so now there's weight being distributed to that top plate. So it only allows 40% of the width, so 3.5 inches times 40% is the diameter of the hole that I can put in there. So that's not very much. And then it says, and here's a bigger one, for notches, I can't notch it out more than 25% of that 3.5 inch 2x4. That's not very much for a notch. So think of that as you look around after the fact, after plumbers, electricians, everyone gone through that, these rules are going to apply. If we notch the top plate, let's say we got to put a big pipe through it. Remember, it's 3.5 inches wide up there. The code talks about this. Imagine the top plate is holding that wall assembly together, okay? If I notch more than 50% of it out, it says I must install a structural strap. Or maybe I put a big old hole in it, a 3-inch hole in a 3.5 inch top plate, most of it's gone. I'm going to have to give some more rigidity to that wall system, so the code says put in this strap. So the strap is in the code. It says it used to be a little different, but it's a 16 gauge strap. They sell these things, and it's 1.5 inches wide, the same width as the top plate, and it's got 8 nail holes in it. They come pre-nailed. If you look at this strap, it's got 8 holes. It requires 8 nails. 8 nails on this side, 8 nails on that side, a total of 16 10-penny nails. And notice it says 8 10-penny nails each side. That's important. That's going to help give that wall back its strength. And so we'll look at that. And there's some other little caveats here I wanted to cover. So this picture tells a lot. It's a couple things. It's wrong. Lots of things wrong in this picture. So if there's a pipe in there, it requires a structural strap if I get rid of 50% of the top plate. But now in another part of the book, it talks about nail guards. So nail guards are protect me from sheetrock and crown molding and stuff like that up here. And the nail guard at the top must come down past the double top plate by a couple inches or so. So you can't take something that's made simply just for a stud or something like that and stick it up at the top plate and call it a nail guard, because it has to go down below the top plate. So they've given us a tool, and I'll show you a picture of that in a second. But what's wrong with this picture? If you look at this, this is good. He's protecting the pipe as it goes through this fire block here. So that's a good use of a nail guard going across. But then he took the same nail guards that have no structural strength to them whatsoever, because it's just, if you've seen it, it's just two little teeth that hold it in there. And he's put it up here as if it's a structural strap. It is not a structural strap. It needs those 8 nails on each side. He did put one on each top plate, but then it goes through, so that's wrong. I'll show you the right one in a second. But then we're going to get into this in a little bit. This is an eye joist, engineered wood product up there, and it says, I can't put big holes in it at the bearing point. And the plumber went straight up, and he made a gigantic hole right here at the bearing point, where all the weight is squishing down on that thing. You can't do that. We'll explain why in just a few slides, but lots of things wrong on this. This is the idea of going into a house, seeing what's right and what's wrong. So we looked up at the top plate. These are those plates, structural plates. So it says I need, if I've gotten rid of a bunch of the lumber, the top plate, I need a structural strap. So now I've got structural straps. If you see, they've got 8 nails on each side, and then it also hangs down below the top plate. So it's a structural strap and a nail guard all in one. So that makes sense. It's a combination plate. Nail guard and structural plate all in one with 8 nails on each side. So these can be used all over the place. Here he's using the nail guard, he's using structural plates, nails on either side of these pipes, so it works. So as you look up at a top plate that's protecting pipes, remember it's got to come down below the top plate. If it's just covering 1.5 inches, it's wrong. It's got to come down below. And by the way, we'll do this in our mechanical classes, but down at the bottom plate also, that nail guard comes up, and it's about this tall, comes up past the sole plate, because they know you're going to be nailing baseboard down along the bottom. So you have the same type of thing. Big tall one at the bottom, big tall ones like these at the top to protect pipes from nails. So I call this old school splices. At the sole plate, what happens when the 2x4s meet? You don't have one giant 50-foot long 2x4 that makes up that wall bottom plate. You're going to have joints in that thing. In the old days, we used to call out and just say, hey, put a stud on top of that seam and just run that up, nail it all into place. That was good to go. That's the old way of doing it. Or some inspectors would call out and say, block between the two and then nail the heck between the two into the existing, and that's good enough. That's old school. If a framer's still doing that, that's not correct, okay? So we're going to look at new things. The code says on anchor bolts, and we cover this in the concrete class, anchor bolts are in most cases not to exceed 6 feet on center. But then it talks about when you have a splice, whether it's in the corner or butting together, those are all splices at a doorway, either side of a door, within 12 inches of the end of this piece of wood right here, there must be an anchor bolt. This one's real good. The superintendent did real good. He punched it out and he said, add an anchor bolt. So they drilled it in, epoxied it in, went with these. These you can tell are in a windstorm area. They're galvanized with square plates, square washers. He did a real good job. Notice they're kind of in the middle third of the bottom plate. So, and they are within 12 inches of this splice that's in the bottom plate. So real good job getting this correct. So no more blocking, no more this is the way you've got to do it. You must anchor bolt at splices. One of the things I talked about earlier is about how houses tend to want to rack and twist. We use a lot of temporary bracing. The code also, as a bare minimum, says we must use 1x4 let-in bracing, simply putting a 1x4 on an angle across a number of studs. Imagine this wall, if that 1x4 wasn't there nailed in place, I could take my hand, push at the top of this wall, and the whole thing would fall down this way. However, now I take this 1x4 and I notch each one of these studs 3/4 of an inch deep, and then I nail to each one of these studs, and all the way it's got to connect to the bottom plate and to the top plate. Again, everything nailed. Now I can push on this, you and I could push on this right here, and this wall would not budge. It is not going to move because there's rigidity to it. Alrighty? So it's one neat little thing. In the old days, we just used to put 2 nails on every stud. Again, the 2018 IRC gives options. At least every connection has 3 or 4 different options on how to nail this thing, depending on what the framer has in his nail gun. So now it's 3 8-penny box nails, so there would be 3 per stud, or 2 8-penny common, or 2 of those 10-penny that I mentioned earlier. So it could be 2 per stud, or it could be 3 per stud, depending on which box of nails he's using. So this is our main thing as far as code to keep a house from racking. So you can see it's very simple. The biggest thing when I'm punching it out is the notch. The notch is supposed to be tight. If it's a 3.5 inch wide 1x4, that notch that he cut should be maybe be 1/8 of an inch taller, and at the bottom, that's it. You don't want an inch on the top and an inch on the bottom and this 1x4 kind of splitting the difference. That would be, hey, let's redo this whole thing. So don't fall for that. If he butchers that 2x4, take it out and recut it. Now then, there's one thing some of you may see from time to time. We call this now portal framing. The code book gets into a lot of wind design as far as a house goes. One of the things we talk about is the garage openings. The garage door, for most intents and purposes, is going to be a 16-foot wide door, 7 feet tall or so. It's a huge opening. But on either side, we might only have this much wall space, little return walls. And then it goes the rest of the garage. So that's not a whole lot of wall to keep it from doing this. Okay? So the code people have said, hey, we recognize this as a problem. So now we've come up with portal opening framing. And it's a series, and I won't get into much detail, but it's a series of strapping and nailing and plywooding, a whole bunch of stuff to make sure that this opening doesn't do this. And with high winds, especially in the Houston area, this could happen. So look for this. What's it look like? Again, on the outside, you're going to see a bunch of plywood with some strapping here and some hold downs, but you'll notice the OSB is cut into the L shape. So they won't block things out. It won't be a piece here and a piece there. It's supposed to be one big piece of plywood cut to the opening. And then there's a very, very tight nailing pattern, I think 4 to 6 inches on center, all the way around that thing. So lots of nails into the OSB as well. So portal framing, look for this on your details. Your engineer may show it a little differently, but there are details in the IRC that show exactly what's needed. But again, it could vary a little bit per engineer. Let's talk about studs. You're going to order some really good lumber. Whoever your supplier is, they're probably top notch, but every now and then you will get a stud that's going to bow, okay? There are some bowed studs, who cares? But before the house gets sheetrocked, the framer and you, the superintendent, should go around the house with a 6-foot level, horizontal, like this guy's doing in the picture, and checking for bowed studs. If one is out, you put that around, it'll trust me, that level will now rock because that stud is bowed outwards. This is important. Why? If I put trim on the wall, chair rail on the wall, if the sheetrock bows out, that trim won't sit right. If I put cabinetry on the wall, if I put a mirror on that wall, vanities and mirrors, very important to have a very flat wall. If I'm putting tile on that wall, I have to have it plumb and flat. So all these things require lots of punch out. So fixing a bowed stud is everybody's job, but how do you do it exactly? So we're going to look at something. So how do I straighten it? Assume you went around and you found a bowed stud in it. One common way that a framer will fix this is he will put a notch into the stud, and then the two good studs that are straight, he'll put a block and he'll push that thing in until it's straight, and then he'll nail it all up, and yes, that stud has been pushed back. So now the wall is now flush all the way across. But what has he done? To get it to push back, what has he done? So you see these in lots of places. And you know, how far can you go before the 2x4 itself starts bowing outward? That's kind of crazy. So I don't recommend what I call the notching method of doing this. Because we look at this thing, remember our notching rules? Can I notch a stud the way they're doing in these pictures? Remember our rules? In a non-load bearing wall and a load bearing wall, 7/8 of an inch of a notch and 1 3/8. A stud, a 2x4 is 1 1/2. So by code, I can't notch that thing to fit a 2x4 anyway. This notch is too large. So when this thing comes in, it's now beyond what we can do. So how can we do this? I call it the plunge cut method. The framer will come along, he'll find the stud, then he'll take his saw and he'll just cut down through it. He won't cut all the way. He'll make maybe a 30-degree angle cut into it. Then as you push on this thing, that stud will move into let's say the plumb position. He'll put his 6-foot level on it, and he'll make it straight. Then he'll put one nail, pow, right through there. That'll hold it. Then he'll come through either with what we call a scab. Most inspectors allow a scab to be used. It's a 4-foot piece of 2x4, and it gets centered on this, and you put a bunch of nails above it, a bunch of nails below it, and that keeps that thing together. Some inspectors may require you to put a full-size stud. If you've cut this one like that, they'll say put a full-size stud just right next to it and just nail it together and we're fine. And that works as well. Very rarely do we actually take a stud out of a wall because it is bowed. But we will fix it, and this is the most preferred method because it's the cleanest, it keeps it structural integrity, and much better for all the way around to pass inspections, most importantly. The other thing I want to touch on is air barriers. Again, nothing to do with the structure of the house, but everything to do with the energy code. When we talk about insulation, insulation must be sealed on all 6 sides. We'll always have studs, top plate, bottom plate. So I've got sheetrock on the other side, so that's 5 sides. But the back side must also be covered. If you go into an attic, for any reason, you see the back side of maybe a game room wall or any kind of wall that has insulation in it, you shouldn't see the insulation. It has to be covered with something that prevents air from migrating through that fiberglass insulation. So we use air barriers. Air barriers can be T-ply, they can be OSB, they can be plywood. In this case, they use excess insulation board. Then the insulation company comes, and when they do the poly seal, they'll seal up all the seams with the poly seal. That keeps air from the attic from migrating through the insulation into the wall cavity and into the house. So air barriers are, again, a framer's job. Sometimes it's hard to see, but it's something that he's got to get used to putting in. So now I want to talk about a few things, what I call special areas. Whenever you're punching out a frame, there's a few areas you need to look at specifically. I mentioned how to check for studs being bowed. I've also talked about briefly the importance of checking walls for plumb. Are they straight up and down? That's nowhere more important than at your tubs and your bathrooms and at your showers, because you're going to be putting a very straight tile or hard surface on that wall. And if it's off a little bit, if it's bowed this way, it's not plumb, the grout lines that are in there will look really ugly. You'll have maybe a real fat one at the bottom and it's flush to the wall at the top or something like that. So you've got to walk around with a 6-foot level, checking everything in key areas. Is it plumb? Are the studs not bowed? And these are things you check as you're punching out the house. So a few things of note. I talk about tubs, specifically the hall tub. Master tubs, there's all sorts of different kinds of master tubs. You're going to have, whatever. But a hall tub is almost always going to be 5 feet long, roughly, and 30 inches deep, roughly. 29 and a half, 30, somewhere in there, depending on manufacturer. And then also the tub, usually it's a 5-foot opening, so the framer makes it 5 foot 0.5 inches, so there's room to slide that thing in. But Look at the tub area. This one's been covered. That's perfect. They've covered it to help keep it from messed up. The house is insulated already. But you'll also notice, so here's the valve wall. One, normal 16-inch spacing for studs would have the first stud being somewhere around 16 inches into this wall. If your tub is 30 inches wide, let's say, perfectly centered would be 15, you can't put a stud right in the middle of a tub opening. So the framer has to know where the tub is. So where the tub goes, he'll start a stud, a little short, then he knows, basically, tell the framer to leave the center part of the tub open with about 12 to 16 inches of space. So that'll allow for blocking to go in and the shower valve, the tub valve to be installed, and then the shower head line to go up, and then the shower head. All that has to be centered on the tub. So if you see a stud roughly centered on a tub opening when you're doing your punch out, it's going to get kicked out by the plumber and something's going to have to be done. So start off and tell the framer, hey, at my hall tubs, here's how this should be and why. So that helps a lot. You'll also notice we call them tub studs. If I have a 29 or 30 inch wide tub, I need to turn a stud flatwise because something unique is going to happen there. Over the tub, it says in wet areas, I'm supposed to have a fiber cement material behind whatever I'm going to put back there, tile or whatever. So I'm going to have that fiber cement coming over, and then I'm going to have regular sheetrock coming over here. And right at that transition, they have to nail together. So where the tub stops, you can see here he's done a great job. Here I'll have sheetrock coming to this point, the fiber cement coming to this point, and I can nail them together. That's the idea of a tub stud. So tubs, a lot of things coming together in one spot. And we've got things called arches. Framers love arches, framers hate arches. But the idea of an arch, they look really nice in a plan. But how do they make them? On an interior arch, or even exterior, they're probably going to be an OSB arch. He's going to look at the plan. He's going to see what kind of arch it is. Some are more arch than others. Some are just maybe kind of a rise. But he's going to look at the plan. It's got to match the interior elevation. So he's going to cut two pieces of OSB to match that. And then you can see here, he's going to put blocks between it. And then he's going to lift it up into place and then nail it in place. That's how it's going to happen. So you'll notice, again, the opening is square, and then eventually the arches get put in. One of your jobs is when you're punching out the house, check the plans to make sure all the arches got put in. Everything's going to go in at 90 degrees. Then they've got to go in and add the arches. So make sure you check the plans to make sure all the arches were installed. And it's a real pain to have to go back and add arches later. And finally, wherever you have cabinetry or hardware, it's always nice to have a hard surface to nail to. Where you have cabinets going in, cabinet blocks in your kitchens, cabinet blocks at the top plate where the bottom is going to be, the bottom part of your vanities, your cabinetry. Having solid surfaces all the way across so the trim carpenter doesn't have to try and find studs is a godsend. So if you can do more of that blocking, have them do it where your cabinets are going to go. And also where your hardware, where your towel bars are going to go, where your toilet paper holders are going to go. That way, again, it doesn't have to go to a stud, and you don't have to use a molly bolt that the service department will hate because those will fall out sometimes within the first 6 months. So tubs, arches, and cabinet blocking, all very important in the punch out of a frame. We come up with this term called pony wall. Pony wall, if I've got, depending on my studs, let's say I've got 8-foot studs and I've got a 10-foot ceiling. I can't make a 10-foot ceiling with an 8-foot stud. So like this picture here, I'll use my 8-foot studs, but then I'll make a pony wall, which goes up an additional 2 feet to get to my ceiling height that's called out on the plans. Sometimes I may have a 10-foot ceiling in this room, and then next door I've got a bedroom with an 8-foot ceiling. That'll be then these ceiling joists coming in on this level. So that needs a top plate here and a top plate up here because I'm accommodating 2 different ceiling joists at 2 different levels. When these happen, you're going to have a space up in the attic that's open. Remember, I'm going up. So here's one ceiling level, here's the other. So this is open in the attic right here. Thus, this framer has added an air barrier to that pony wall. And he's cut a little slit in the OSB that can be spray foam with the poly seal. but at least he's put it up there. It's very hard to add air barriers later, notching around all these different members. So air barriers first, put the members up later. What happens if that pony wall is actually up in the attic? The pony wall is here on that last slide. It was just between two rooms. We could see it. But let's say you have a big, tall elevation in the back, maybe a covered patio, and they've raised from the top plate of the family room up, maybe an additional 4 feet, so you have this big, tall patio for patio cover out back. This is very common, but it's just another pony wall. But now remember, what happens to this wall up there can it move? And we're going to see in a little bit, yes it is. So pony wall, if they're freestanding walls like this, they need to be addressed. So go up in the attic and have the framer add some bracing that goes to structural members. Whether it be back to a wall, a beam, some other members, but you want to get that so that wall doesn't move. How does that move? We'll show you here in a little bit on some additional slides when we talk about the roof. But pony walls, if they're in the attic, must be braced back into the structure so they don't move. A different kind of wall that tends to want to wobble is our little half wall at the top of a stairway. If you look at these pictures, over here, here's the stairway coming up, and then we got this little half wall that eventually will have a nice finished cover, a plate on top. It'll have maybe a handrail going down on it. But if you were to get at this end of it, you could grab the top of it and shake it back and forth and back and forth. And some guys will say, well, when we sheetrock it, it gets stiffer. No, you sheetrock it, it gets stiffer, but in a year, service will be out there fixing it because it wobbles. Kids go flying around half walls. Kids sit on top of these things and it will rock. You cannot expect this to be structural if it's just simply nailed down into the plywood subfloor. Those are not going to keep it from doing this. So you've got to make these half walls. If there is no column going here, if there was a column going up to the ceiling, that would work. That wall ain't going to move. But when it's freestanding, just like a peninsula, you've got to do something. So here's that wall. And what they'll do normally is they'll take one of these studs. They'll simply cut out the subfloor and some of this. There's a wall down here. And they'll take this stud and they nail it into the structure down here. Nail and block it into the structure. That way, this top wall will never move. So if you're up there on a frame punch and it moves, not good, get it fixed. Most common fix is to run it down into the structure, block it, nail it, tie it in so it'll never move for 100 years. This is a nice little article. The Journal of Light Construction, which is a magazine I recommend for all builders and home building. It's very inexpensive, but it's a great magazine, whether it's hard copy or digital. Get a copy of this, become a subscriber. It helps us with all sorts of things. And this particular article that I mentioned is about fire blocking. Fire blocking is one of those things that it's hard to envision, but your inspector will nail you on almost every inspection before sheetrock because he says, add fire blocking at. You're like, well, where does that come from? There is an entire section in the code book about fire blocking and draft stopping. If you want to read that, it gives you an idea. But most of the things are, if a fire can get into this wall and transfer up into another place and get up into the attic or another space or the floor system, you need to stop it in the wall. How do you do that? Well, we put blocks up here, or plywood, do things to keep the fire contained in wherever it's coming from. Excuse me. So that's what they're showing us here, whether it be a kitchen fur down, they show here, just block it, put some 2x right in there before you build your fur down. That creates a fire block. We'll see some examples at here they put a block here coming up. So if the fire comes up, it can't get up and in there. Very common. But fire blocking is tough to see or envision. But as you do more and more frames, you'll see where this goes and you'll see it happening. So here, there is a rule that if you have, let's say you have a tall ceiling. Let's say you've got a big game room or a family room with a 12-foot ceiling. The code does say that in a stud cavity, no more than 10 feet can go up that stud before you got to put fire blocking across there. So if you got real tall walls, a balloon frame at a tall entry or a back wall with lots of glass, you'll see 2x4 blocking put in. That's to keep fire from traversing up maybe that 20-foot tall wall. Here It's kind of like that example we showed earlier in the sketch where he's got one ceiling down here, another room up there, and to keep fire from this wall coming into this cavity and up into that floor space, he's put plywood, at least 3/4 inch OSB plywood, or you can use 2x material, but that will work as a fire stop. And then there's other places that are called out specifically in the code book. If you've got a stairway going up, next to the stairway, there will be 2x4 blocks put in these walls going up, all the way segmented. If someone has knocked one out during the mechanical phase, it's got to go back in there before you have your inspection. Then if you have a mechanical closet, well, let's say a water heater in there, obviously you've got this fire block here. Any chase down here in the house that communicates straight up into the attic on frame punch, if you look up and it's just, you can see the attic through that chase, then they're missing the fire stop on top. Again, 2x material, 3/4 inch material, something up there to stop fire from going up that chase into the attic. And then finally, around a chimney. A fireplace is a great place, that's the most obvious. We build a fireplace and then we've got these walls on usually 4 sides of the fireplace. You'll have to fire block all the way around that, usually at the plate height. Where's the ceiling? That's where the fire blocks go, because that's where the fire could go there and into the attic. So it all makes sense when you see it in 3 dimensions out in the job, but fire blocking is a very important thing that you've got to look for when you punch out the house. So let's talk about flooring systems. I'm going to talk about all sorts of choices we have. I'm going to talk about how this goes in, some good practices and bad practices. But let's see what happens, and we'll keep building this house up. So when it comes to floor system, there's lots of choices and lots of vocabulary that we need to talk about. Some things will just be second nature. Some things will kind of be a huh kind of thing. But when it comes to framing a floor in a 2-story house, you've got to have a floor system above your head. It used to be our only choice was 2x12s. Now most people don't use 2x12s because 2x12s tend to squeak and shrink and bow and do strange things. So 2x12s have almost always been replaced by something that I'll show you here in a little bit, like floor trusses. Floor trusses are engineered wood, so are eye joists. Eye joists, we'll see some examples, are just that. It's a solid piece of lumber top and bottom with an OSB-like material in the middle. Very, very tough, very strong, and can make great spans. The taller the eye joist, the more of a span it can cover, and it really opens up a house. Then OSB plywood for our subfloor. A minimum subfloor is 3/4 inch, all the way up to 1 1/8 inch, and they're all usually tongue and groove now. But that plywood, what do we do? Do we just nail it? Or before we put it down, do we put a subfloor glue on top of the joist and then put that down and then nail it? And then before the glue sets, do we take screws and we screw that down just to make sure it's as tight as possibly can be? Those are all questions that every company has to have. Do we use ring shank nails versus just straight nails? All sorts of things come into play. Framing systems, hangers, joist hangers. It's nice to have the joist hangers on the purchase order there when you need them, as versus being a punch out later, like add joist hangers, and we'll see some of that in a little bit. But and then what does the stairway look like? Is it a curved stairway? Those take a lot of time. Are they straight stairways, U-shaped stairways? And how and when are we going to get this thing in? So lots of questions to do with a 2-story house when it comes to floor systems. So the floor joist. The joists are the things that we're going to put the plywood down on top to make our floor system on the 2nd floor. Or if you're doing raised floor construction in flood zones, this could be your 1st floor, but it's a floor system. So I talked about 2x12s. Here are the floor joists I mentioned. Again, made in a factory, shipped out. And then eye joists. Eye joists to me are my preferred method. They're, for me, easy to work with. I don't like 2x12s anymore just for that. Plus 2x12s are expensive. But eye joists seem to be the way the world is going. So all these things, though, need special attention. When you're using them, floor trusses, eye joists, they all have their own special rules. Your framer needs to be familiar with them. Then going forward, your mechanical trades need to be familiar, the do's and don'ts with some of this material. So like when we use dimensional lumber for joists, it's kind of a fuzzy picture. I can't clear it up, but it just gives the point. it's in the middle of a room and the plumber's gone through and out of a 2x12, he's cut out about 6 inches of the wood right in the middle of the room and with a Sawzall. Can you do that? No. But this guy, he destroyed the whole thing and had to be reframed. It's a, again, fuzzy picture, but you just got to know the rules. And he was confusing the rules with I joists with the rules for dimensional lumber. And there's different rules. So let's take a quick look at dimensional lumber rules first. Notches. We don't notch much on, if we're using a 2x12 floor joist, we don't notch much, but just to know, it is in the code book. These are right out of the code book. And if you were to notch, whether it's down here on the bottom or up here on the top, if you were to notch it, it tells me I can't use more than D/4. So the actual depth, remember 2x12 is actually 11 1/4. So that over 4 gives me my maximum notch. And then same thing up here, D/6 for notches out here in the outer thirds. I can make a notch, but nothing's permitted in the middle third. Very, very simple. But again, we don't notch much, but we do make holes in I joists in 2x12s. And here the code says 2 inches minimum from the top or bottom of the joist. I have to have 2 inches of wood on, above or below it. And then I can only have D/3. So again, 2x12, what is a third of that? Well, I have an example for us. If it is a 2x12, what's the maximum hole? If it's D/3, remember it's 11 1/4 times a third is 3 3/4 inches of a hole. A plumber, for a 4-inch pipe, technically it's not going to work. For a 3-inch pipe, he could do that. But for a 4-inch, he can't. So that's how you can get these things figured out. But that's for dimensional lumber. For I joists, the rules tend to be kind of totally opposite. Depending on your manufacturer, all sorts of companies make I joists, but they're going to give you something like this in their instruction manual. It's online. It's in their instruction manual that comes with the package of I joists. Your framer has copies of it. There might even be details like this on your plans. But the general rule of thumb per manufacturer is toward the sides, there's this no hole zone. And it says for X amount of feet, no holes except the little knockouts that they put in there in the factory. Maybe you can run a wire or maybe a 3/4 inch pipe through it. That's it. Those little knockouts. That's it. You can't add your own holes, can't do anything. And then 2 to 3 feet in, you say, okay, now you can cut a 2-inch hole, and then a 4-inch hole, and a 6. In the middle of the span, you're allowed to cut out the entire piece of OSB material in the middle. An air conditioning guy might do this for a duct. That's very common. Some people go crazy. Homeowners see that and think the world is ending. But this is what it's designed for. In the middle of the span, you could take out the entire middle because that's technically where there's no load. And you can run a duct through the middle. You can't take that same hole and put it over here where it says the 2-inch hole can go. You can't do it. That would require an engineer to write a letter and you might end up replacing floor joists. So know the rules. So, and it does vary. I just had 2 examples, a 16-foot one span, a 12-foot span, but generally biggest hole in the middle of the span, the holes get smaller as you approach the ends, and then at the ends, within 2 to 3 feet of the load-bearing portion at the wall, you can't put any new holes. So those are the rules for I joists. Review these with your AC guy, your plumber, your electrician. Because again, your framer is going to give you a great looking frame, but then someone's going to destroy it because they don't know the rules. Some folks will look at an I joist and think you can't cut them, they're just straight cuts. I just want you to know most manufacturers have a deal where you can cut them at an angle. This usually happens maybe at a garage. There's a game room up there or whatever, but maybe you have a sloping roof. And at the end, obviously it can't stick through the roof with a 90-degree corner from an I joist, so they allow you to cut them at an angle. There are details, so here's some. You'll notice these plates. They use OSB or plywood, and you are allowed per detail. Again, it may vary per manufacturer, but they'll show some sort of nailing and gluing of plywood on either side of that web of that eye joist. It'll be on both sides. They glue it, and then they nail it all the way through, and that becomes a stiffener on the end. So you can cut those eye joists at an angle. Most of them will say, hey, here at the end, I need some sort of wood left. You can't cut it down to zero. Can never cut it down to zero. It's got to be, it's usually 6 inches or so here, and then you can cut it at an angle. So, but it'll be covered here in their charts that they give you on their website or in the instruction manual. The other thing about eye joist is there's always now a rim board that goes around the perimeter of the house. The rim board helps take a lot of weight from the second floor. Eventually the plywood will be put on top, second floor will be built on top of it, and that starts squishing the eye joist down below. That rim board, which is usually at least 1 inch thick, sits up there. It takes a lot of the weight from the floor upstairs and transfers it to the top plate down into the slab. But that rim board has to be treated nicely. In the IRC, there are 4 choices of nails that you can use on a rim board. Rim board has to be attached. First of all, you have to nail to the eye joist itself. When he puts it up there, the eye joists are there, 1 nail. If you read the instructions, almost every manufacturer says through the rim board, 1 nail goes to the top flange of the joist and 1 nail to the bottom flange of the joist. That's it. Not 3 or 4 or 5. Doesn't mean the more nails, the better it is. 1 nail top and bottom. You don't want to make Swiss cheese out of the connection points of these things. So then it says, well, in the code book and in the manufacturer's instructions, it says you shall add nails going into the top plate. Okay, because a lot of that pressure coming down, you don't want it to pop out. Okay, so they say, hey, either at 4 inches on center or 6 inches on center, you're going to add a bunch of nails to that rim board going into that top plate. So again, those you can see on punch out before they cover it with whatever your house wrap is. So look for that if you have a 2-story house. Then comes the subfloor itself. So we've got the eye joist, the floor trusses, the 2x12s, whatever they are down. I've got a rim joist around if it's eye joist, but we're ready to add the subfloor. Subfloor nowadays is almost always some sort of OSB, oriented strand board, and engineered wood. It's almost always tongue and groove, which means there's a groove at one end and the tongue on the other piece, so they fit in together, and it's very simple. And they're always 4x8 for the most part, so the spacing is critical. But when you see your framer doing this, I like to see subfloor on the joists, or subfloor glue on the joists, lay this thing down, put it in place, nail it and screw it. That's my preferred method. I also look from underneath to see, you've got to see glue somewhere in the assembly. You've got to see glue oozing out somewhere. It's just part of the deal. If you don't see any glue, you got to question your framer. Hey, are you really using the glue I sent out here? Because it should be used. That's part of the assembly. But then if you see them when they're up there and they put down one piece and then they get to the next piece, some framers will put a block of wood down there and they'll take their sledgehammer and they'll smack that piece of wood into the other piece of wood. So the tongue jams into the groove and that pops that up. And that becomes a problem. The manufacturer says these are just supposed to slide together and there should technically be a joint, roughly about 1/8 of an inch, maybe 3/16 between pieces of OSB. And this is on all OSB. Subfloor, roof deck, the stuff you put on your walls for sheathing, shear walls, all OSB needs 1/8 to 3/16 between its adjoining members for expansion and contraction. Now the subfloor will want to pooch like this, which creates a real problem when you want to finish your floors later on. So they should never be smacking the pieces of plywood together with a sledgehammer and breaking up that tongue and groove connection. So look for that when they're placing it. One thing that comes up on inspections for subflooring is the flooring itself. If you're using 2x12s, an inspector said, I need bridging up there. They'll write your red tag, I need bridging. For all intents and purposes, in most houses we build, bridging is not required. If you kindly give a copy of the code book to the inspector, it says joists exceeding a nominal 2x12 require bridging. Okay, and it tells you what bridging is. There's the code section. But we don't have anything exceeding a nominal 2x12. We don't have a 2x14. So bridging is not necessarily required for dimensional lumber. So I find that kind of inquisitive in the code. But hey, stranger things have happened. Joist hangers. Occasionally, when we put our floor joists up there, we're going to butt into a ledger or a beam or something that requires a joist hanger. We're going to nail into that beam or nail through that beam, but a structural member just can't hang on nails. Never, ever, ever do you expect something to last 100 years just hanging on nails. It's, gravity will take it and want to pull it down. So we put a joist hanger underneath it. And these are all pictures of joist hangers in place. Very nicely done. Big one. Here's a giant 3 or 6 inch wide beam with lots of nails in this massive joist hanger. Some other ones here. Here's a giant one over here that actually takes bolts to hold it in place. So joist hangers for dimensional lumber, for beams, they're very common, but you can't deform them. If it's if you get a 2x12 hanger out on the field, you can't smack it a little wider to fill a 2-inch manufactured beam and expect to pass inspection. Every joist hanger is made for the exact thing that it's holding. Dimensional lumber has their own joist hangers. I Joist have theirs. Floor trusses have theirs. Manufactured beams have theirs. So don't jury rig some sort of joist hanger because your inspector will fail you. And the other rule is, if you see a hole in a joist hanger, the general rule is every hole gets a nail. So if he just tacks it up with one nail on each side to start, hey, that's a start, but he's got to come back in later and add nails in every single hole in that joist hanger. That's how they're rated and tested. So if you see nails missing, tell your framer, hey, on your punch out, add nails to joist hangers. And again, I mentioned, know your joist hangers. Joist hangers for I joists are a special beast. They're just made for I joists. Can't use them for 2x12, can't use them for a floor truss, but they're made for that. They usually will go over the top of the beam or whatever it is they're hanging from, and then the I joist gets slid into it. If they tack up the I joist first and then put the subfloor down before putting in the hanger, it's wrong. Some guys will cut off that tab that goes on top and call it a day. Joist hangers for I joists have to go in before the subfloor goes down. That's all there is to it. And they're going to be adding nails to the tops of those joist hangers because that's what helps it stay on that beam. And then there's a few more nails, very few nails on the bottoms of these things. So those nails on top are crucial to making this thing work. So we've talked about walls, we've talked about our floor systems, talked a lot about our frame. Let's say in our 2-story house now, we've got to take a quick time out and talk about the stair to get up to that second floor. A lot of times on an inspection, stairways will throw a kink in your game plan because an inspector will focus on stairways because there's so many rules to remember. When we're looking at this real quick here, just know a few things. If you're walking up a stairway, your feet will tell you if they're right or wrong. If they're leaning backward or forward, your feet will tell you that. The code actually says a walking surface cannot exceed more than 2% of a slope. So if you're walking, again, and you feel that's very small in a stairway. So catch it at punch out. It's easy to shim up a tread, if it's just one tread, or a stair, fix the angle on it, to get that 2% or more taken care of. But it's real tough to do after the house is finished and on your final inspection, the inspector says you've got too big of a slope on your treads. So 2% is all you're allowed on a walking surface. So let's talk about stairways. Generally, they're almost always made out of dimensional lumber. We usually have, these are stringers. Stringers are made out of 2x12s and they cut all the little angles into those 2x12s. And you have 2x4s running down the sides and that creates the gap to run sheetrock down and then put your trim, which is usually 3/4 of an inch, down alongside of it. If you shimmed right up to, or came right up to the stair, none of that stuff would fit and you'd have to be cutting it all. So this is how things get in. Also note that at the floor, if it's concrete, you can't have pine lumber, regular pine lumber, touching concrete. Our Soleplate, our bottom plate, is always going to be treated lumber. Anything that touches concrete needs to be treated lumber. So obviously these stringers can't be just regular wood, they've got to be treated lumber. So I'll show a treated lumber sill plate underneath it, then secure that to the slab, then secure your stair to that, and life is good. So these things are great. And the three rules kind of, every tread, the minimum tread, measured from the nosing above it, is minimum is 10 inches. Okay, that's a tread, the thing you stand on. Then the riser, no more, maximum is 7 3/4 of an inch. 7 3/4 for a riser is the maximum. You can't have an 8-inch. The maximum is 7 3/4. I can have 7 1/4, but not 8 inches, or not even 7 7/8. That's more than 7 3/4. 7 3/4 is the maximum. So treads are 10, no more than 7 3/4 there. But there's two rules here. I call it the law of 3/8, the rule of 3/8. Whether it's the tread or the riser, and I'll use the riser as the example because an inspector will go up every stairway with his tape measure and he will measure every riser on your stairway. He's measuring one to make sure you don't exceed 7 3/4. Then he's also making a mental note. What is the smallest riser on this stairway? And then what is the tallest riser on this stairway? If my tallest riser is 7 3/4, anywhere in that flight of stairs, I can't have a riser on here that's 7 inches, because the rule of 3/8 is within that entire flight of stairs, no tread or no riser shall be more than 3/8 of an inch more or less than any of its neighbors on that stairway. So if I've got a 7 3/4 maximum at the top, I can be 3/8 less than that anywhere else down below. Remember, it can't be above it, but I can be below 7 or 3/8 of an inch. So be careful when you're measuring. Again, if you've got a 7 1/4 and a 7 3/4, you're off. You're more than 3/8 of an inch, so you will fail that inspection if you measure your stairway. So remember the rule of 3/8. Most framers are aware of this, but understand what the inspector is looking for when he measures each individual riser and tread going up the stairway. Here's a picture of the underneath of that stair. That, as we look here, the treated lumber is underneath. There's a lot of subfloor glue holding this in place, and it's secured. You can see some bolts holding the treated lumber to the slab, and that's what we're looking for when we look under there. You don't want the stringers going straight down to the concrete. If it's on plywood, you're working on raised floor in a flood zone, that's fine, it's on plywood. Those rules don't apply. It doesn't have to be treated. And just briefly, as we build up this house, know that what we talk about in Texas is platform framing. Just a term that's used. We have a platform. We start with a slab. Then if it's a 2-story house, we'll have a second floor and then a roof. But that platform, we start on that upper deck flat, then we start a new wall on top of that. In the old days, we used to use balloon framing, which means from the slab all the way to the roof would be one open wall system. That's not what we do anymore. Sometimes when we have a 2-story window wall in the back of a family room, that's technically balloon framing, and that's why I was mentioning earlier that you have to fire block because it's such a tall bay of studs. So we're dealing with platform framing, that we're talking about all these parts and pieces as they fall together here. So as we go forward, so now we've talked about walls, subfloors, stairways. Now let's talk about the roof system. Most of us in Houston, or all of Texas for that matter, we kind of got 2 different types of roof system going on. Usually it's going to be a hip. A hip is a roof where we've got it's a point at the top, and then the sides kind of lay over, and they kind of lay over too. And so we've got these 4 leaning sides. 4 leaning sides of our box here, that's a hip roof system. When only 2 sides slope up to a pitch, up to the ridge, and the ends are triangles, let's say, that's a gable. So we've got gable roofs and we've got hip roofs, and then we've got combinations of each one in between. So some are easier, but that's usually what we're going to have. If you have a flat roof, I don't want to talk about it because flat roofs, especially in Houston, will leak. But hips and gables is what we're going to look at as we talk about framing. So here's a very simple garage plan. Here's a garage framing plan. I can tell it's got a simple ridge, and it's basically a hip roof all the way around. Leaning, 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 leaning. But you'll notice on the front here, we've got some more framing going on. So I've got a gable facing the driveway. That's a very common kind of thing, kind of a look. So I can check that on the frame. So now I've got a house here, with, let's say with an attached garage. And you'll notice now at this end, I've got a gable because there is no hip being shown, no triangle, no leaning roof. It just goes straight out. That's a gable end as shown in plan. Then it comes along, here's my ridge. And then here, this is leaning in. You can tell by our hip here coming up to the ridge. So I've got this roof leaning in, and then we're taking a 90-degree turn. In the back of the house, we've got this hip coming here. So this is a hip, this is a hip, but at that end, we got a gable. Just different looks for different plans. But you can tell just by looking at the roof plan what you're going to be getting. So when we look at the plan, these are the parts and pieces. Again, know the terminology. I won't spend a lot of time on this slide. I may blow it up here on the screen and talk in the background. But what I'm talking about are know the terms. Common rafters go from the top plate up to the ridge board. Okay. When you talk about hip jack, they're the ones that hit the hip rafter. They don't go all the way to the ridge. So they're the shorter ones. What is the hip? What is the ridge? What is a valley? Anytime I take a 90-degree turn on a roof system, I'm going to create a valley. And so the valley comes from there, the valley rafter, and then hip, ridge. It's all part of the vocabulary to make you a better professional so we can talk about these things like we actually know the terminology. So we framed up our house, we've got our walls, and we've got our ceiling joist to all our rooms down below. This is a very simple plan. Imagine a house, okay, we framed it up, we got the walls and the ceiling joists in place. The ceiling joists have a job to do, okay? We don't think about that. Remember that nailing schedule I talked to you about? Nails make a difference because here comes a roof, okay? What does a roof want to do? Think of Mother Nature. Think of gravity, okay? The second these rafters are applied to these top plates, they want to push the walls out, okay? I've got the ridge up here, and then I put rafters like this on an angle. Gravity wants to push down on that ridge and push those rafters down and push those walls out. That's just what gravity does. And you could see this on some houses. If you look at some older houses, you look down a long 50-foot wall on the outside, and you'll see it bowing outward. That's the roof system pushing out on the walls. Why? Because maybe we didn't have a proper ceiling joist system. All those nails, nailing to the top plates all the way across, where they splice together, nailing them together instead of butting them up to each other. Their job is to hold the walls up. So they run a continuous system all the way across the house. That's the idea. So the joints are spliced and nailed. They're nailed to the top plates, nailed to the top plates on the outer part, on the inner walls. Everything is nailed down to keep those rafters from doing what they want to do, push the house apart. When they come down again, so they're running with our ceiling joists. Where the ceiling joists and rafters come together, life is beautiful. They all line up and you can nail them together. But sometimes they go against the grain and we have to add some jack joists in here. We'll see a picture of that in just a second. But the idea is to help keep the walls up as the roof wants to push it apart. So here's a picture of the jack joist. So all the regular ones are running this way, and then here at the end, we've got to tie them in. So we're going to tie all these rafters that are running this way to a jack joist. That's nailed to the rafter. That's nailed to the first ceiling joist in here, and that's how we combine them. Okay, so every time if they're running parallel to each other, they line up, you nail them together. They're perpendicular, you've got to have a jack going out and tying into the ceiling system in the first room that ceiling joist is in. So when I talk about roofs, we talk about roof pitch. You'll hear them talk, they'll throw around terms. The pitch is 412, the pitch is 612, 812, 712, 1212. All this stuff, it's just, what are they talking about? It's for every foot of space, I'm going up so much. So a 412 pitch. In 12 inches, I'm going up 4 inches. In 12 feet, I'm going up 4 feet. That's a 412 pitch, okay? So on this chart, I've just shown a very common thing. You can get this off the internet, you can get this on anywhere, but it shows the common pitches. A 412 pitch, pretty flat. It's right in here, not even 20 degrees. But if you start seeing a common thing would be a 6 or an 812 pitch, you can see it starts getting pretty high. It's more of a 30, 35 degree pitch. So that's getting steeper. So a 45 degree pitch is what? 1212. 1212 is a 45 degree roof. That's a pretty steep roof. If you got to walk on a 1212, please be careful. I don't wish anyone to walk on a roof. Leave that to professionals, leave that to roofers, leave that to guys that are meant to walk on roofs. You don't need to be up there. But just know how we measure a roof. So now your job is to check. You're looking at the house. How can you tell if the framer put the right pitch on a roof? Sometimes you can tell by the details. The plan, maybe often drawn by a computer, is so accurate. Maybe it shows 12 inches underneath a window at a dormer, but there's no inches at the dormer underneath the window. That might mean the pitch is too high. So how do I check it? Now, the only plug I give in this video, something I have on my phone, is Roof Pitch Factor for my phone. I have used this countless times. I can't go on a roof and put a thing and, yes, they make gizmos, but the easiest thing for me is to go, I can go into the attic, I can reach out a window on a dormer, I can get to a roof a number of ways and put my cell phone on that thing, and it'll tell me what pitch that roof is. Just by putting my phone on that angle and on the screen, it'll tell me. I can take a screenshot of that and send it to my framer. The other neat thing about this program is just like they're showing in this picture, is I can be standing on the street and I go, that roof pitch doesn't look right. And I could hold my phone up with Pitch Factor on and I could take a picture of that, and there'll be a line on my screen. And I will line that line up with the actual roof pitch, maybe of my gable. And I will take a picture of it then, and it'll show a picture of, just like it's behind me here, it'll give me the actual pitch of that roof just by taking a picture. And I can send that to my roofer, my framer, whoever needs to know that, hey, we might have a problem here. So if you're supposed to get a 612 and you get a 412, there's a problem. Discover that before you put shingles on the house. Punch out the house, walk around using your phone, and you can check the angle of a roof. It's just that simple. So let's talk more about parts and pieces. We've got our walls, we've got our ceiling joists. And remember, they're being nailed here at the exterior walls, interior walls. They're nailed all because they're keeping the roof from pulling it apart. So we've got our rafters going up, our rafters going down. We've got a collar tie up here. What is a collar tie? People think, well, that helps it from pulling apart. And no, in reality, the ceiling joists are helping it from pulling apart. The collar tie at the top is for uplift. We think of, a hurricane. Winds come and it wants to pull the roof up. And that collar tie between two rafters help resist that. It's a pretty neat thing to have. It's one of the smallest things we have in our framing system, but very important. And then it's got a number of nails. A minimum of 3 nails, again, per the 2018 code up there. It used to be 2, but look at the nailing pattern for collar ties and it'll show you. And then we've got our ridge up on the top. So now, what if my ceiling isn't on the top plate? This happens a lot in our master bedrooms. Maybe we've got a raised ceiling and now we've got these sloped ceilings on the side, and so we're not sitting on the top plate, but it's up a few feet. Those are great, wonderful. Just make sure your framer knows all the parts and pieces. It's now not a ceiling joist, technically it's a rafter tie. It's keeping those rafters from pulling apart, but it's still doing its job. Make sure he's got the right amount of nails here to keep it from pulling apart. So it can be done. And just for fun, I'll superimpose this on the screen here when we're doing the video, but here are just a few examples of ceiling joist to plate, collar ties, rafter to plate, rafter to ridge, all the different types of nailing requirements for roof assemblies. And there are more in the book, but I just put a few of them up here because the most common nail that we're going to use, like I said, is that 3-inch .131 or 10-penny nail. Those will be your most common things that you're going to use, but it's the number of them. How many? Just make sure you see nails. So now here's one of those raised ceilings. Master bedroom, and this framer's come in here, and I can see a bunch of nails installed, so that's good. But some inspectors will say, hey, where you nail that thing up there, since it's not sitting on a top plate, I want you to support it all the way down to the top plate. Some will say, I just want you to scab it. These represent some scabs that could be put in, or you could take some there and nail it to the existing rafter, cut underneath that ceiling joist, which is now a rafter tie because it's off the top plate, and carry that down to the top plate. So again, very good project. So when we talk about roof systems, obviously we want to talk about rafters. Rafters are the things that create the roof itself. Pretty simple idea. Usually in Texas and Houston, we stick build. So we're going to have rafters, usually made out of 2x6s. If you've got a clear story, maybe a cathedral ceiling, you might have larger members, 2x8s, 10s, 12s, something like that, depending on how big your cathedral ceiling. But for the most part, we use 2x6 rafters in most of our houses. That's allowed by code. That's wonderful. I want to use an example here from the southernpine.com, Southern Pine Inspection Bureau. The ones who in Texas, we use a lot of southern pine because that's what grows in our forests. And these are the folks that rate how good our stuff is. If you go to their website, there's a series of charts that tell you how far this lumber can span. I can look up floor joists for certain things, 2x8s, 10s, 12s, whatever. I could look up rafters, ceiling joists, floor joists. All these things are in here in multiple number of charts. I chose the one for rafters because this comes up most often. Because if you get an inspection that says you have overspanned your rafters, where do they get this from? This chart, number 41, is the most commonly used. It's for rafters, 20 pounds per square foot live load, 10 pounds dead load, and with a deflection of L over 240, which is a technical term we won't get into right now. But this is what we use to figure out how this will work. So when you look at this chart, there's two columns here, and I'll come over here, 2x6s is the very top, and then usually, depending on your spacings, 16, 19.2, or 24. If you're at 24 inches on center, and I'm using number 3 lumber, I can have a span of 8 feet 4 inches for a rafter. Or if I'm using number 2 lumber, I can go up to 11 feet with the same 2x6, but a better 2x6. So the 3 is the lowest grade, number 2 is the higher grade, number 1 is the best grade, although I've really never seen number 1 used for framing. So this is what we can use to come up with this. So for the most part, 8 to 11 feet is what you can span with a rafter. So obviously we have rooms greater than this, so how do we span this and still meet code? So let's look at that. Keep that in mind. So now we've got rafters. So we're making this roof system. We talked about the collar tie, the ridge, ceiling joist, rafter tie. One thing, rafter to joist, how many nails go in here? This amazed me. This just amazed me. I asked many city inspectors, how many nails go here? And there's a little known thing in the code book, table 802.52. It's a formula of how wide is the house, how flat or how high pitched is the roof, loading, all sorts of things go into this formula. And then it spits out how many nails you will need for this connection. So it figures out how much force is being pushed outward on those outward walls. And so now they're saying you will need so many nails to help keep this thing all together. The shocking thing to me was, if you look at the chart, 3 to 39 nails are required for this end connection. That's incredible to me. Most of ours, when you look at the charts, It's usually from 4 to 7 nails per connection for most typical things that you might see around Houston. It's not as extreme. You need big snow loads, big stuff like that to get up to that 39 nails per connection. But for us down south, 5 to 7 nails is a pretty good average for that connection. So we're building this roof up, and so now I ask the question, hey, can I have a ceiling with no joists and no rafter ties? So if I got rid of no ceiling joists, no rafters, no collar ties, could I? Yes. But then it becomes a cathedral ceiling. And just so you know, a cathedral ceiling is something a little bit different. Yes, you're going to need deeper rafters, like I said, maybe even 2x12s. And then this ridge board becomes a ridge beam. That might be a structural beam, maybe 3 inches thick, maybe even more, depending on what the situation is. But that's up to an engineer to design. So keep that in mind. Yes, we can do cathedral ceilings. We can do all sorts of things with ceiling framing. So what is a span? If you get an inspector sometimes, private inspector sometimes will say you have overspanned your rafter. And you say, well, what's the span? Now, how did you do it? You cannot count the number of pieces of plywood on the roof deck while standing in the attic to come up with a span for that roof. That's not how you do it. It is not measured on the diagonal. That is not the span. Span is measured from the bearing points, from the bearing wall to wherever the next brace is. Maybe it's the ridge, maybe it's a purlin brace. Wherever it's being supported, that's the span on a horizontal plane. So if you're punching out a house, you put your tape measure on the outside wall, you measure inward, you look up at the ridge, and if that's the only span, look at your thing and remember, if it's number 2 rafters and you see 10'6", you know you're fine. Remember, because you used that span table. If you're using number 3 lumber and it's 10'6", you've overspanned that 8'4", so you have overspanned it. But know how to measure span in rafters. And so again, that's either from the wall, the bearing point, to either the ridge or to your purlin brace. And so by going from wall to purlin brace to ridge, now I can do a system that works. So the other thing that's in the code says the rafter shall have full bearing at the ridge. So when you have a flat roof, maybe a 412, a 2x6, when it's cut at the ridge, it usually fits up there if it's a 2x8 ridge. But the more angle you get, let's say on a 12-12 pitch, even a 2x6 cut at that angle, you get a really deep heel right here at the top. And sometimes it looks like this. It doesn't quite meet that ridge board up there. And the inspector will say, you don't have full bearing at the ridge. Don't panic, you don't have to reframe the house. Most of them will then just go back in and you add, usually a 2x2 will do, but you can go in and nail that up to there and get that full bearing in there. But it's just something, if you've got a 2x6 rafter and a 2x6 ridge, chances are it's not going to work. It's always at least one size larger, but as the pitch starts getting deeper, it might be 2 or 3 sizes larger. So look at that as you start framing, and look up at your ridge when you're punching it out. Alrighty, one of my favorite drawings used to be in the code book. This drawing is from one of the older code books, but in the 2018 they replaced it with like a schematic of an entire house. But I like this because it was an actual drawing of purlin bracing. Purlin bracing saves us when it comes to sagging roofs. If you have a sagging roof, you have probably a purlin problem. You've overspanned your rafters, or he didn't put any purlin braces in there. Something is wrong with the roof and you got to jack it up. But purlin bracing is what allows us to get longer spans out of a 2x6 because it's sitting on the bottom or top plate over here. But then as we go up 8 feet or 11 feet, I got to put a purlin brace in there to support it because then I start another span and go from there. So what are the rules for purlin bracing? So a purlin, if the rafters are coming up this way, I want a purlin brace that's braced this way. So opposite direction of whatever the load is coming to. So in this case, this is a great deal. It's usually a 2x4, okay? 2x4 is going to come up and we're going to go up to the rafter and meet it. The maximum rafter span per table. What is it? I got to look at the table and know where this purlin brace is going to go, because I have to know if it's 8'4", I'm going to measure a span of 8 feet and say, hey framer, that's where the purlin brace needs to go. Most architects and designers know these rules from the span tables, and they'll show where a purlin brace needs to go for the framer. Framer shouldn't have to guess, but we should know then the purlin, the actual horizontal piece, this piece right here, is the same size or larger than the rafter itself. So same size. So if it's a 2x6 rafter, the purlin has to be a 2x6 or larger. If your rafters are 2x8s, your purlin has to be a 2x8 or larger. Okay? There is no all purlins are 2x6s. That's not in the book. It has to be the size of the rafter or larger. That's the purlin itself. Purlin braces are no more than 48 inches on center. So this thing coming up, that's the brace. That's the purlin brace. This is the purlin here. Sorry, going that way. Purlin brace nailed to the rafter. That goes down to a wall or a beam. Okay, so I've got that, but it says no more than 4 feet on center. So figure that out. If I've got 24-inch spacing, that's every other rafter. So that's 48 inches on center. If it's 16 inches on center spacing, that's every third rafter. So does that make sense? So you've got to know what your spacing is to know when you're just looking up there, or you can go up and measure, but no more than 48 inches on center. Again, I mentioned to a wall, and then not less than 45 degrees. This one shakes people up. So the angle of this 2x4, again, I use pitch factor for this. I'll put my cell phone on these things, or any bracing in the attic for that matter. They mentioned not less than 45, not less. So here's 0 up to 45. So 30-degree angle, 60-degree, something, no. So if I'm got my brace this way, I can do a purlin brace straight up, down to 45. I cannot go down below 45 and expect that brace to be worth anything. So from 90 degrees to 45 is my sweet spot on any purlin brace, or any attic brace for that matter. So that's part of our rules for purlin braces. Then an unsupported length of 8 feet. That means this 2x4 cannot exceed 8 feet. So from there, well, I got some tall attics. Then you just simply make a T-shape out of it. That's supported. Whenever you make something a shape, an L or a T, that makes it much stronger. And again, guess what? In the fastening schedule, it tells you got to nail these things together. So make a T-shape out of this rather than just a normal straight 2x4. You'll notice when they get real, if you got a 12 or 16 foot 2x4, they wobble like this. So the code is saying, hey, 8 feet's where we're going to say. After that, you got to start making it a T so it doesn't wobble under the weight of the roof above it. So some very good rules for a simple bracing system. So what do they look like in the attic? Look for them. You can see them from down below. So here's the purlin brace nailed to the rafter, comes down to a beam over here, and then it is a T shape to give it a little added rigidity. So that's good. Here's a T shape. Here he's using the T to help support the purlin itself, and then the purlin brace is nailed to the rafter. Good work on these purlin braces. And then here you can see a line of, so this is 24-inch spacing, every other rafter. Purlin brace goes up, nails to the rafter, purlin's running across, and he used this T shape to come across and nail everything together. Some good practices. So you can use lots of things in purlin bracing and feel comfortable in that. Another brace that's often overlooked is what I call the saddle brace or the palm brace. And again, make sure you understand where this goes. The code book says at the conjunction of the hips, valleys, and ridge, where a hip or valley and the ridge all come together, you shall brace it. That's it. It doesn't say how to brace it, it just says you shall brace it. And in this case, this is the most common thing you'll see. Again, it's a long brace. He used a 2x6 with a 2x4 T. So it's a long way up in the attic. It's probably 12 or 14 feet tall. And then he used a piece of dimensional lumber and he nailed that to all the pieces coming together. So he's got a hip and a ridge, and it all comes together and he's braced it. and then it goes down to a wall. That's great. He's also got another brace back here, T-shape. So he's done a really good job of bracing this roof. Now remember, look at it, and does it make sense? So if the force is coming this way, I want a brace that pushes it back that way. If it's backwards, if the force is this way, and I got a brace going off this way, it all wants to collapse. So make sure the brace makes sense, that equal and opposite reactions. So wherever the force is, you want a brace that goes against it. So palm braces, saddle braces, they're really good. When we're looking at a roof, sometimes from the outside, some things don't seem so evident. But whenever I look at a roof or a plan, when you have changes in pitch, if I go from an 8/12 pitch to a 4/12 pitch, I'm coming down the bobsled run and then it's flattening out. Okay, so something, the lumber just doesn't miraculously do that. I've got to do something up in the attic to make that happen. So I would normally go in, if I see a house like this going from an 8/12 or 10/12 to a 4/12, I would go in looking for something supporting that junction, because I'm going to have one at a steep pitch, one at a flat pitch, nailing them together, but then I need something underneath it to support it. So when I go in there, I look up at that area, and here's what I see. Here's the flat pitch, here's the steep pitch, and there's a beam supporting the upper steep pitch, but nothing supporting the lower pitch. Does that make sense? So when I see that, the only thing holding that lower pitched roof, and remember, the lower the pitch, the more force it creates, so I need more nails. I see 3 nails holding that to that for 100 years. That's not good. So it would have been better if this beam caught both of these together, then that's okay. Or in this case, now I'm going to need a beam underneath the top end of the lower pitch roof as well. So that will hopefully work out in the end. So changes in pitch, make sure you got those covered. Now, some things are not always in the code book, believe it or not. People say, show me in the code book where rat runs and strongbacks are talked about. Well, they're not. There is a line that says you shall properly brace a frame, and that's really where these things have come from over the years. So rat runs and strongbacks, what are they? A rat run, I don't know why they call it that, it's just called that way. When I have ceiling joists, if you look at a ceiling joist, maybe you go up in the attic. If you see ceiling joists, they go along and they just end. Okay, they just end, there's nothing beyond it, they just end, and you think, well, gee, what keeps them from falling over? That's a really good question. So that's why we put a rat run up there. It keeps them all acting as a system. Okay, so here's some ceiling joists. They just end, because now we got a lower ceiling over here, and so we've got some ceiling joists that just end. Now we're going to come along and we're going to add a rat run. Rat run could be a 1x4, could be a 2x4, could be a 2x6. It doesn't say what it needs to be. It just says we're going to put that so all those little dominoes that are stacked up in the attic won't do this over time. Make sense? Pretty simple idea. And those go at the ends of ceiling joists, okay? So look toward the end of ceiling joists. Some of the ceiling joists are going to tie into rafters. They're going to be nailed to the raft. They're not going to fall over. But maybe it comes into here 14 feet and it dead ends. That's where I would need a rat run on the inside. So that's a rat run. We look here, here's again ceiling joists, they kind of end, rat run at the end. I tie them all together. Now let's talk about strong backs. What's a strong back? That's not me, it's not my back for sure, but strong backs will be in the middle. So I've got ceiling joists going over this room. On the ends, I might have rat runs at one end or both ends of those ceiling joists, depending on what they tie into or don't tie into. And then in the middle, I'm going to have at least one rat run. In a normal room of, let's say, 12 feet, 13 feet wide, you might have one rat run in the middle, or strong backs, sorry. Strong backs go in the middle. But if it's a wide, maybe it's a big game room, maybe it's 16 feet wide, you might have 2 strong backs off center, but normally you're going to have one in the center. And what is this thing doing? So as you look up, and again, it's going to be a structural shape. Almost always going to be an L, okay? It's going to be a 2x4 with a 2x6. Again, remember an L, all nailed together, it's not going to bow. It's a strong structural member. So that becomes my strong back. Here it is if I'm looking up in the attic. Here's my L, 2x4 with a 2x, nailed all together, sitting on top of my ceiling joist. You can imagine now, as I look at the ceiling joist from below, if there's a gap between the ceiling joist and that strong back, the framer will push that ceiling joist up and nail it in place so it doesn't sag. That's the idea of a strong back, is to help the ceiling system stay at one plane. So if you have sagging ceiling joists, this thing, the structural member, a true structural member, will hold it up. Now, with this thing, it has to be tied in at least to one end. Again, keeping the racking thing from happening. It's out in the middle, so it's going to tie in either to this ceiling system out here or into a rafter over here or a top plate or something, but the one end of a strong back will be tied into some other part of the job. So strong backs, very important little thing, so look for them in almost every room. So we're looking in a room, looking at the ceiling system, I'm looking up in the attic, I say, hey, so a Purlin brace system is resting on this beam. So I'm happy that they've added a beam to support the roof, and then that comes over here, and you'll notice they will always, when you have beams, if it's two 2x12s or a double beam or a 3-inch wide beam, you always want to match the minimum number of studs with that width. If you've got a 4-inch wide beam up there, put at least 3 or 4 studs into that thing to match that. Most inspectors will look and they just want it to match the beam above it to support it all the way down to the slab. So that's the first thing, support your beams properly. In this case, this is supporting the roof. My ceiling is one thing. These things will have sheetrock on it and that'll be flat forever and ever. The framer has added a 2x4 for this beam. So it's now 1.5 inches above the top plate, which means it's higher than the sheetrock up on the ceiling. So if that Purlin assembly up there puts weight on that and it sags a little bit, let's say it sags 1/2 inch, it's well above the sheetrock to the point where the sheetrock isn't going to sag and look kind of weird with a sagging ceiling. So that's why we block up a beam like this. So if it's supporting the roofing system, always try to have the framer block up the beams so they're 1.5 inches higher than the rest of the ceiling. Sometimes you can't block up a beam. In this case, this beam is part of this actual ceiling. So the beams, the ceiling joist tie into this beam, and you'll notice over here this beam is not blocked up because again, it's at the same height of the ceiling. So if it sags, everything sags with it. But this beam is sized by an engineer to minimize the sag. Again, engineered wood beam is engineered to minimize sagging. So that's a great thing to have. So these will be great. So you also notice there's a rat run happening out here. So some good things happening. So we've got a raised beam right here. And this beam is supporting a roof system that's independent of the ceiling system. And we've got strong backs coming in the middle of the room. And then, what's this? The framers come in and he can't cut the beam out of the way, so he runs the strong back into it. And then if you go up, he's actually nailed the strong back to the beam. So now I've created a problem, or the framer has actually, but I catch it on punch out. I like to see a little 1/2 inch gap right here minimum, so I can see that they're not connected. Because think about, the idea of the strong back is simply to keep all the ceiling joists on the same plane. It's independent. The ceiling is independent of this beam that's supporting the roof. So now I've tied it, I've nailed it to that, so as the shingles and the weight of the roof get applied, this beam sags, and now all the ceiling joists have to sag because this beam is taking it with it, and the whole ceiling is now sagging because it's tied to this beam. So on punch out, simply just say, hey, cut the strong backs loose from the beam in the family room or whatever it is. And that'll save you a sagging ceiling down the road. Finally, as we look at some of those beams get really big. They might be 18, 20 inches tall up in the attic. Again, when you're punching out, you check your plans, and if it says beam for ceiling support, roof support, whatever, here's a beam supporting a Purlin brace system up in the attic, and it's two engineered wood beams nailed and glued together. And you'll notice though, it's not an optical, it's kind of leaning, right? So if it's leaning that way, guess what's missing? You say, well, shouldn't we brace those things? So again, if I'm thinking, okay, if it's leaning this way, shouldn't I brace it this way? So that's what we want to do. We want to come in here and on punch out say, hey, add diagonal bracing at beams above family room or whatever that is. Again, if it's being braced, if you see bracing this way, that's absolutely useless. Useless, because the weight wants to push it over, and you got to put bracing the way the weight is coming. You see those Purlin braces up there? It's already pushing it that direction, so you want that brace to support it all it can. So kind of important, look at your beams, make sure they're properly braced. Now, I kind of tease and say, is there an alligator in your attic? And sometimes there are. On hips and valleys, sometimes those things get very long, and we can't help but have to have a splice in them. They're different than the ridge. I'll talk about the ridge in a second. But valleys and ridges are going to be usually 2x10s maybe, but you're going to kind of put them together. And we're going to cut a V shape in one, V shape at the end. We're going to fit them together like a giant alligator. Okay? But the way they're shown in the details is not like these things. These things in attics, you can see they're all falling apart. These are not good. You don't want these in your attic. So those are bad, these are good. Usually your engineer or your designers will give you a detail on how to do an alligator splice, but generally you're not going to see the alligator splice. But where the framer puts one, he's going to put an alligator splice somewhere in here. Then he's going to cover it up with OSB on both sides. He's going to glue it and then nail it. And then underneath the splice, he's going to put a brace down to a wall. That's how it works. So here, OSB, brace, works. Very, very nicely done on those two examples. So this ugly stuff you never want to see. So look at the detail for alligator splicing on your plans. If not, discuss it with your framer and say what you're expecting to see when you see an alligator splice. Finally, as we start winding this down in framing class, some people ask me, hey, is this guy a good framer or a bad framer? And all of you as professionals should be able to figure this out in probably 5 minutes. Walk into any frame. If you're just driving around, you're driving subdivisions, you're driving construction, just stop in and look at the frame quality. And what do you look for? Within 5 minutes, you can tell if this framer is really good or not. Look at the details, all right? So I start looking at details. Miter joints and connections. If they're good and tight and properly nailed, then it's fine. Here, you start seeing gaps. There's not supposed to be any gaps. If you can stick a credit card between two pieces of wood, that's probably okay, but tight is tight. If you see it's tight at one end and a big half-inch gap at the bottom, the angle's been cut wrong. So you want all the miters to be cut and cut well when you walk into a house. So these, I give them a failing grade. And when you walk in and you see things tight, I don't see any daylight in these miters. I don't see any miters, and they're properly nailed. Remember, more nails doesn't mean a better connection. If a guy misses an angle cut, rather than put 3 or 4 nails like the code says, now he puts 10 or 12 nails because he figures, well, it doesn't really fit, so I'll just put more nails in there. That's not right. So give some credit to where things are done well. And so here, look at the bracing. How does he brace stuff? Just look at the brace. Does it make sense? Is it clean? Does he take everything into account? That's what you're looking for. How are his bird mouths cut at the top plate? Are things tight? Has he overcut things? Has he undercut things? Are things all lining up? When you walk around the outside, look at the plane of the roof. Do you see sags in the rafters? Or maybe the roof deck's on. Does the roof deck sag already before the shingles? Remember I talked about the ridge. Alligator splicing on hips and valleys have this alligator splice, remember? But at a hip, or at the ridge, the very top, you can butt those things together. So at the very top of the house, if they're butted together, how do you brace those? And normally you're going to see that that's a good thing for a framer to check. He's going to have a brace right underneath that seam, if you will. And sometimes they'll put maybe a 2x2 and they'll nail it, maybe it's a 4-foot piece, and they'll nail it across, and then they might put a brace on either side, one for each piece of ridge, and then carry it down to a beam or to a wall. That's what you're looking for. So different ways of bracing things. The idea that he's taking all the weight from that roof down through the system, through walls and beams, down to the slab. Has he carried it all the way down? So this is what you're looking for when you're grading a framer. And then finally this, look at the house. Every day, I tell our guys, every day by the time you leave, it should be immaculate. Here's a house, it's just after they're finished framing, and this house, you can almost eat off this floor. It's clean, it's tight, all the trash is in the dumpster, everything's been punched out. It's a good job. This is something anyone would be proud of. Your boss would be proud of if you walk this job. So that's what we're looking for in our trades nowadays. One thing we didn't mention is clips and straps. In the Gulf Coast, and even now in other parts of the state, the wind codes go as far north as the Oklahoma border in Texas. That cities are requiring stronger and stronger winds, some in tornado-prone areas, and obviously some in windstorm areas. There's 14 counties along the Gulf Coast that require windstorm protection for the Texas Department of Insurance. You'll notice here on the screen, I put this note, new windstorm starting September 1st. It was supposed to have started in April, but they pushed it back to September. And it's basically saying the wind provisions of the 2018 IRC will now be the TDI, or the Texas rules for windstorm along the Gulf Coast. So if you know the 2018 IRC, start flipping through. There's a section for wind and wind design. That's what you're going to have to be familiar with. But basically what we're talking about is you're still going to need an engineer along the coast to design this, and he's going to tell you, hey, you need clips and straps and hold downs and anchor bolts with big square washers. And so get to know the rules. If you build in Galveston County, Brazoria County, parts of Harris County out near Baytown, out toward Beaumont, if it borders the Gulf of Mexico, these rules will apply. But you will learn about all these big hold downs with lots of nails in them. You'll learn about clipping and strapping up at the rafters. And what we're doing is we're taking a continuous load path. The idea is, okay, we've anchor bolted the bottom plate to the slab, but in a windstorm, everything wants to lift off that slab. So sometimes you'll just have the Soleplate left after a hurricane. But with clipping and strapping, the idea is, okay, I'm going to start at the bottom plate on this side, and I'm going to clip that to the first stud, and the top of the stud to the top plate, and that top plate to the rafter, and that rafter to the ridge, and then that ridge to that other rafter, to the other stud, to the other bottom plate. And so I've created this envelope of metal ties. And if you take that times 360 degrees around this house, that house is now solidly held down to that massive slab that you put in the ground months ago. That's the idea of clipping and strapping. So it's a lot of work. And when you look at it, it gets kind of overwhelming when you look at all the nails and the parts and pieces. But windstorm contractors that put in clips and straps, your framers that handle these on a regular basis, they know where they go. So get familiar with windstorm rules wherever you're building so you know what will apply. For winding this down, I don't expect you to read this on your monitor, and I won't have this up here long. Maybe I can email it to you. But punching out a frame. I ask guys, when do you start punching out a frame? The day that guy snaps that chalk line is when you start punching out a frame. Don't say, I wait to the very end. That's too late. Imagine the day when your framer doesn't have to show up after the mechanical trades because everything went so well. He doesn't want to have to come back and send his crew off of another job just to come do punch out for you so you can get an inspection. But the day he chalks those lines, our pipes out of the walls. Maybe you make some executive decisions. Do you fur out a wall at a commode to get it back in? Do you move a wall slightly to adjust for something being out? And then when he flips up the first outside walls, maybe he just gets up the outside walls that day. That afternoon before you go home, you could say, I'm going to check all those exterior windows, sizes and locations to make sure they're in the right place. Your framer comes back the next day and you say, hey, you got 2 windows in the wrong place. And then he says, oh, if you do this all along the way, measure those risers on the stairway before he leaves. When he does the second floor, as soon as he puts up the outside walls, as he's working up on the roof, go by in the evening when they're gone and check the walls on the second floor, and eventually the roofing system. And then before he leaves that final day, have everything punched out, and before he rolls up the hoses, so he gets everything punched out really tight. So then in an effort that very minimal punch out after mechanicals, whatever, maybe he sends 1 guy to maybe add some clips and straps, who knows. But punching out all along the way makes for a very happy framer. You may think you're bothering him, but if he doesn't have to come back, he'll work for you for a long time. So just get to know, if you want to start a punch list, if you want to have a multi-page thing on your iPad or whatever that shows, these are my checklist items, first floor, second floor, stairway, major points, roofing, develop something. And that's what all these are, is just basic stuff that you can get from either your company's checklist, or give me a call or write me and I can get you this stuff. But it's just checklists to help you look for stuff. Especially if you're new, you don't know what, don't try and keep everything in your head. Use a checklist to make sure your frame is going very well. And like I said, this is all small print stuff. You're not going to see it. But have a checklist system, because as you go through, it's your job to check every aspect. That's what the ABCs of home building is all about. Not that the trades punch out their own work. You have to check everything. You are the final authority of what's right or what's wrong. So every opening, every frame, every door, window, everything in a frame, you're checking as it goes up. And by the time we're done, you put your final check mark and you call for that inspection before sheetrock. And when the city inspector comes in and he's got nothing on his list and you're walking right beside him and he gives you a green tag and he says, man, you've done a really good job on this frame. That's the best feeling you can get. Your boss is happy because you get a production move, but you've probably gained a week in your production schedule because you didn't fail that inspection. So the frame, other than the slab, the frame is the most important thing that you're going to punch out when you get this thing going. If you have a good slab and a good frame before sheetrock, that's what will make your life easier and production will go much quicker. If you're having to move things and fix things later frame-wise, that's a disaster. So I hope you've learned something watching this video. Again, I'm Dave Yelovic, and I'm glad to be a part of the online learning series here at the GHBA. I hope you come by the GHBA in Houston to join us for a live class, or continue to watch us online. And I hope you'll continue to learn the ABCs of home building.